Okay, I want to remind you real quick what this means. So you have basically on the first formula, what it's trying to say, what the formula is actually saying is, you have a graph, right? And there's two functions graphed on the same graph, and you're trying to find this area between the two functions, like so, between two values of x, say a and b, like that. And you can see that one function is sort of above the other in this region. So we would call this the upper function and the lower function. And to find the area between here, you can just think of the height as u minus L, see? So the height is u minus L, like that. And the width, of course, is just some delta x. We went over this yesterday. And so the area is u of x minus L of x times delta x. And if we take the infinite case, where we stack an infinite number of these, all infinitely narrow in here, this becomes a dx. We get an integral sign, which really represents like addition. Really, an integral is really just an infinite sum, is all it is, of an infinitely numerous amount of infinitely narrow objects. You could think of it that way. So there's your integral, and of course it starts at a and ends at b. And then the other one, does anybody remember what this one's used for?
Sideways. Sideways.
Sideways, right. So you can see I made a mistake here. This should say dy. Sorry about that. But basically it's whenever your graph looks more like this, and you can't decide which one's upper and which one's lower. It's more of like this one's on the right. I'll make it thicker. So the thicker one is to the right, and the thinner looking one is to the left. And now it's the width that's r minus L, see, right minus left. So this is r of x minus L of x. The height is delta y, and the integral basically runs between y equals c and y equals d. And to get this area, you would need to do r of x minus L of x. You should say r of y and L of y, sorry. And you multiply it by delta y, you'd integrate because it's the limit, and then you're done. So anyway, we were just doing this example last. I know it's messy, but that was our last example. We got 4/3. Okay, let's try this one. So what I'd like to do is pause my recording and let you try this one, because it turns out you can actually do this problem both ways. Like you can do either formula. So try whatever first comes to mind, and we'll see different people are actually trying different things here. Okay, so let's say that you wanted to treat this as an upper minus lower type function. Okay, the problem with that is if you draw a sample rectangle in here, okay, the upper curve is clearly y equals x squared, and the lower curve is, I guess, y equals 0. Okay, and that is true for this first part. So basically your upper curve is y equals x squared, and the lower curve is 0. Once you get past x equals 1, things change a little bit. Your upper curve is this line now, and the lower curve is y equals 0, see? So you would have to do this in two phases. You would have to first integrate from 0 to 1, and you would do upper curve minus lower curve, x squared minus 0. And then you would run the second integral from 1 to 2, see? This time, y, of course, is 2 minus x. The upper curve is 2 minus x, and the lower curve is 0. So it's really two integrals if you do it this way. Try now. You should get 5/6. Antiderivatives were easy, right? 1/3 x cubed, that stuff's not hard. And you're only plugging in 1s and 2s and 0s. zeros. Not too stressful.
When you do it right and left, you have to isolate x.
Yes, you do. Yes, you do. You need x as a function of y. That's right. Okay, so if you decided to do the problem this way, you have the red integral and you have the blue integral. And the reason is upper function changes roles there. The curve is on the upper side and then later on the line. Anyway, if you plug everything into this, you get 5/6, right? There's a totally different approach on this problem. Did anyone do this problem a different way?
I'm trying.
Okay, I'll give you guys a couple minutes to try it a different way. Perspective. Okay, so let's say instead of using that last method, you want to think of this as your sample rectangle here. Imagine sketching rectangles in like this. These are more stacked vertically. See? And you're using a rightmost point minus a leftmost point to get the width. Delta y is your height. So you're using this integral instead. Rightmost function minus leftmost function, integrating over y. We're going from c to d. Y equals c would be this line. Y equals d would be this line up here. In other words, 0 and 1. Okay, so we're going to go from 0 to 1 and just integrate that direction. Okay, so this is better because throughout this entire blue section, the line is always on the right of the curve. So that's actually a really good way to do it. You can do it all in one integral. So we'll just do this curve minus this curve. But first you have to isolate the x's because you need to enter them as expressions with y's only. So if you isolate x in the one on the right, it's going to read x equals 2 minus y. And if you isolate x on the left, you technically x equals, if you isolate x on the left, you get square root of y. It's technically plus or minus, but you can tell we're only in the first quadrant, so there's no reason to have x being negative. So we would just assume it was just rad y, and that's what you would use for your r of y and L of y. You would use 2 minus y minus rad y. Okay, so here's your integral 0 to 1. You have 2 minus y minus rad y. And this works out great too. This gives you 5/6 as well. Let's try it. Your antiderivative is 2y minus 1/2 y squared minus 2/3 y to the 3/2. And you're plugging in 0 and 1. Plugging in 1 gives you 2 minus 1/2 minus 2/3. Plugging in 0 gives you 0, 0, 0. So basically you have 5/6. It's 6/6 minus 3/6 minus 4/6. Okay? So that works, doesn't it? How many of you did it the first way? Second way? Okay, you think you might need to know both methods? Probably, right? Okay, let's look at this one. Find the area bound by the curves. Sometimes you don't really know which method you're going to use until you draw it yourself. Okay? So I would like to have a graph of this, but I don't really want to graph it on my calculator. That feels like cheating a bit. Does anyone know how the square root of absolute value of x would look? What would that look like?
Just the top here.
Look the same.
Well, square root of x, I always tell my pre-calc students, square root of x looks kind of like a helicopter taking off. Helicopters start off by rising, and then they take off into a certain direction, right? So I was telling that because I want them next year to know that there's a vertical tangent at the origin. That's why I tell them the helicopter goes straight up. Okay? We haven't talked about slope at all in pre-calc, but that's the graph. What does putting an absolute value of x do function. What does that do? Changing the x to an absolute value of x. Because this is just rad x. This is not the full effect, you know? This is y equals rad x. What does putting the absolute value x do? Okay, yeah, this is a strictly one-sided graph, right? It's only got a right-hand side. But by putting in the absolute value of x, we can now plug in negatives. We have that freedom. So you could plug in like -1 and it would give you +1 now. If you plug in -4 and it would give you +2. In other words, what happens is this right side reflects over and forms a second half to the picture. Okay? By the way, this is always what happens with this situation. Y equals square root of absolute value x forms two graphs. Y equals rad x and y equals square root of negative x. In other words, a reflection over the y-axis. And they're both together like this, and that's the graph. Okay? Now the other thing is the line y equals 1/5 x plus 6/5, which is no big deal. We can graph that. Looks like that. Okay, so here's the thing. We're trying to find the area bound by the curves. So the area is actually right here. Can you guys see the yellow? I'll use a little bit different color. Let's use this orange. So we're trying to find this area and this area, see? So I have a couple problems with this problem. First, I would hate to integrate that square root of absolute value x thing. Like, I can't stand that. So I probably won't. What I'll probably do is I will avoid integrating that guy. And I will integrate on this side of the y-axis when I'm over there. And I'll integrate on this side when I'm on the other side, see? I'm not going to actually integrate across the origin. There's no way. I'm going to build the antiderivatives. Okay? The other thing is, I don't know where these points of intersection are. Like, I don't know where the points connect, you know? I can't even get boundaries for my integration. You know, I'm going to be integrating from somewhere to somewhere, but I don't even know what those points are. So that's like top priority. I got to figure out where these three contact points are, see? Okay, well, it turns out they're all very easy to guess. Can somebody just give me a number that makes this true? Why don't we multiply by 5? It might help you to visualize it better. 5 square root of absolute value x equals x plus 6. Can you think of a number where if you square root it, absolute value, square root it, multiply by 5 is the same thing as adding it to 6? Not 1, that would give you 5 equals 7. Negative 1. Negative 1 gives you 5 equals 5. It works. Okay, so x equals -1 is a contact point. Is that what you said?
Yeah.
Sorry, I thought you said +1.
No, I said negative.
Okay, yeah, -1's definitely a contact point. +1 doesn't work. Yeah, let's try numbers that are easy to square root, right? So 4, does it work? It does. 10 equals 10. Beautiful. So this is at 4, evidently. So you can see my drawing's not quite to scale, right? Can you think of another number that this works for? 9. Yes, 9 works. 5 root 9 is 15, and 9 plus 6 is 15. Okay, so I really didn't want to solve that thing like algebraically, but the roots were pretty friendly. Okay, so, or the solutions. So you can just basically draw this with more accuracy. So I actually kind of need to re-sketch. So back to the drawing board. Let's put our contact points on now. So we have the point 1, 1, and we have the point basically 4, 2, and the point 9, 3, and this curve can erase this old stuff. And I've got this line. So line goes like this. Okay, so I'm actually going to do this in 3 phases. Okay, it's definitely an upper minus lower sort of thing. It's not a right minus left in my book. I'm going to treat it as upper minus lower throughout the problem. So I'm going to stand up a little tiny rectangle right there. See? And the upper curve is the line, and the lower curve is the left half of y equals absolute value square rooted. So basically what I'm saying is this is the line, obviously the top is the line, and the bottom curve here is actually square root of negative x. See? Okay, so my first integral is going to look like this. Integral of the line minus that lower curve. And this is only true between -1 and 0. So I'm going to put limits on here, -1, -1, 0. Not -10, 0. -1, 0. Okay. When I get to the y-axis, I'm going to switch my mind. I'm going to still treat the line as the upper curve, but the lower curve is now rad x. See? So your little rectangle standing up in this space. So the green one will be, and we're integrating from 0 to 4 now, integral from 0 to 4, upper curve, that's still the line, minus lower curve. That's just square root of x, regular square root of x. And one more integral, and that's between 4 and 9. Between 4 and 9, the curve is the upper function, and the line is the lower function, see? So I'm going to have to integrate between 4 and 9, where the curve is the upper function, and the line is the lower function. So you might be frustrated with the fractions, but because of the 1/5 and the 6/5, we actually got the nice limits of integration. So it's a payoff, a trade-off. You're going to have to find these 3 integrals and add them together. And since I'm too lazy to do that, I will tell you the answer. Which, of course, comes out to 5/3. Obviously. Get the popcorn. Okay. So obviously the answer there is 5/3. What about this one? Find the area bounded by the curves. Again, a chance to practice sketching first, right? So I would just go with whichever variable is easiest to isolate. You know, like on this problem, it's really easy to isolate this. And you could just think of this as y equals -4x squared plus 4. And the other one, it's easy to isolate y as well. Y equals x to the 4th minus 1, see? So if y is the easier variable to isolate, then by all means, do it that way. And you just want to double check that you know where everything is crisscrossing. So you kind of still need to sketch it out. The red graph here is, let's see here, the red graph, it's a parabola. It's opening down. It has roots at plus or minus 1. That's especially obvious if you factor it. Okay, so it's definitely crossing through here and here. It's shifted up 4. Okay, I don't think this is a big deal. This is the graph of the red. And do you guys remember what x to the 4th graphs look like? They're basically like parabolas, but they're a little boxier. Like they're not quite as, they're more like a U than a V. And this is just shifted down 1. This one also has roots at plus or minus 1. Okay, so after seeing it, I realize, okay, I know this is like one of those cases where the red curve is always above the blue. See? And the upper function is always the parabola, and the lower function is always the blue quartic. So it looks to me like we could just do this in one integral. We'll integrate from -1 to 1. The upper function minus the lower function. Maybe you want that in parentheses, right? Prevent any negative errors. There we go. So it's all one integral. And you know, this isn't that hard to do, but notice how the green area is the same on both sides of the y-axis. So do you guys remember how I cheated yesterday and made my work a little bit easier? Okay, I used 2 and I integrated from 0 to 1. That way I'm only plugging in 0 in the end. So I'm going to integrate from 0 to 1 and I'll just use my symmetry to my advantage. So I'll do 2 times the integral from 0 to 1. Because most of my mistakes are in this arithmetic at the end, you know? There you go. Now it's one integral, and it's 0 and 1 as your limits of integration. Pretty easy to work with. Okay, let's see if I can do this one really fast in my head. I'm pretty sure this all comes out to 104 over 15. Which evidently is one of the funniest numbers ever. That and 5/3. Okay. 104 over 15. It's nice teaching PC because I don't have to go through the steps where I find the antiderivative and plug in the 0 and the 1. Right? You guys got it now. Good. Uh-oh. So look at this function. It's not a function, it's a relation. It's not even going to pass the vertical line test. This thing's really funky. It's not a function, it's funky. It's a function. So, what are you going to do with this? If you can't graph it, right? If you can't graph it, you can't find the limits of integration. If you can't find the limits of integration, you can't set up your integral. It's a problem. So what are you going to do? You're going to have to find a way to graph it. Fortunately, it's really easy to tell when x would be 0, right? So x will be 0. When will x be 0? Just look at it. Don't try to solve it. Don't square both sides and use trig identities and Mama's theorem. Just look at it. What values of y would make this true? 0, pi over 2, pi. Any multiple of pi over 2 would make this work, right? Because you've got a cos y and a sine y. And when cosine encounters pi over 2 or 3 pi over 2, you can go to 0. And when sine encounters 0 or pi or 2 pi, it's going to go to 0. So basically, every factor, every multiple of pi over 2 is going to make this work. All right. So x is 0 when y is any multiple of pi over 2. Okay, so let's see what that would look like. That's interesting. That's going to form a ton of different y-intercepts. So for each pi over 2 on the y-axis, x is 0. Even when y is 0, x is 0. When y is negative pi over 2, x is 0. So you got all these here, and these are labeled in pi over 2s. See? And these are your y-intercepts. Okay, the curve is also kind of interesting in that it only contains certain pieces. Why? Because when cosine is negative, we can't square root it. So we have to stay away from angles like between 90 and 180 and angles between 180 and 270. They're not going to exist. So this is a very strange graph. It's a fragmented, weird wave thing. But look further into the directions. We are only interested in y goes from 0 to pi over 2 anyway. So we don't even need that upper piece. We're just focusing on that lower piece down there. Okay, so now it's time to kind of re-sketch just what we need. We're very focused on this spot only. Zoom in. Okay. Zoom in. So here's what we got. 0, pi over 2, a little bump like this. See? And if you keep reading, it says you're finding the area between x equals 0. Isn't that just the y-axis? And this curve, that's the red, between 0 and pi over 2 for the y. Yes, that's all. So just this area is, the whole time, that's the whole area right there. It wasn't really that complicated in the end. So I think we should use right function minus left function. Red minus green. See? All right, so let's do that. Our integral runs from y equals 0 to y equals pi over 2. It's the rightmost function, which is x equals 3 sine y square root of cos y. So 3 sine y root cos y minus, and then we have our left-hand function, which is just the x equals 0 line, so you could just put 0 there, I guess, dy. And before you grab your calculator, this is a simple problem if we use a U-substitution. So which one would we maybe want to make our u? Sine or cosine? Okay, so if you make your sine your u, then you will get a cos y dy for your du, but I don't see a cos y dy anywhere. I see a square root of cos y dy. I think we should make the u our cosine. And that way we'll have a du rad u sort of thing. Okay? All right, so you can always play around with it, right? Or if you're really desperate, get out your calculator and do math 9. Okay, but I'm going to let u be cos y. Therefore, du is negative sine y dy. Or you could, some of you like to isolate dy. That's kind of cool. I noticed some of you are doing that. You can isolate dy and stick it into your integral. Or I just like to look at this and say, I see a sine y dy here. Oops, just erased it. I see a sine y dy. I just don't see a negative. So I'll write this as negative du equals sine y dy. And that means that this is basically the integral 0 to 3 pi over 2. And then there's a negative, and it's basically root u du, like that. I have no idea why it's 3 pi over 2. It's just supposed to say pi over 2. Mr. Shore just sometimes writes random 3s. Okay? Okay, so it's not, you don't have to use a calculator on this. Yeah, question?
Don't you have to substitute the ends back in?
Yeah, I'm going to keep them as y values, but just so I'm not tempted to use them yet, I'm going to label them y values. I won't plug them into a u expression. I'll replace my u with y, with cos y before I use those. Okay, so I'm going to basically go antiderivative phase, actually. So that's going to be 2/3 u to the 3/2, right? And we're going to be plugging in y equals 0 and y equals pi over 2. Can't plug them in yet, though, because that's a u, not a y. Looks like my 3's cancel. Okay, so I have basically negative 2 cosine y to the 3/2, like that. And I'm supposed to plug in pi over 2 and 0, see? So that's not very stressful. If you plug in pi over 2, the whole thing is 0. If you plug in 0, the whole thing is negative 2. So the answer to this is 2. Go figure. 2, whole number. Kind of neat. And I just can't resist going up to my cool picture and putting a big fat 2 in that space. My area is 2. Hard to believe, but it's true. Okay? And then this one, you just have to draw everything very, very carefully. All right, so here's y equals x over 4. Yeah, question?